Hello friends, today we're going to solve quantum mechanics paper C-11. I have already made part 1, link is in the description. So this is part 2. So in part 1, we have solved from question number 1 to question number 3. Actually there were 2 questions in 3, so you have to solve one only. So I have already solved the first one in the first part. So today we're gonna start from the next part of this question number 3. Okay, so this is for the BSc5th SEM student, Dibrugarh University. So now before we start, please subscribe the channel if you are new to my channel and hit the bell icon so that you get notified when new video will be uploaded, and share with your friends and hit the thumbs up button. So now let's start. So in the last video we have solved this part of this question number 3. So here either you have to solve these questions or you have to solve this. So now let me explain today this, and this is also question number 3. Okay, the next part. So from here we're going to solve today. So here you see this is the given function I have written here. This is the given function, and we need to find the expectation value of momentum. P is momentum here. So how to find the expectation value? This is the way we can find the expectation value. Integration psi star, this is momentum operator psi, then dx. So this is the momentum operator, and psi star means the complex conjugate of psi, and here you see. So I have replaced this p cap, that means the momentum operator, by h cut I del by del x here. Okay, so now let's replace this psi by this given function, right? And psi star will be also same, because here you see we have only the real part, so its complex conjugate will be also same. So we have put those values and integrating from 0 to L, because the region is given here. So I have assumed that you know the integration, so that's why I'm not going to explain here how I have integrate. So here 2, and here apply the 2 sine a cos a, that is sine twice a. That formula is applied. It's very simple trigonometric formula. Then and integrating this, I have got this, right? Now let's put the upper and lower limits. So we have got this result, and so cos twice n pi, that's going to be equal to 1, and cos 0 is also 1. So that's why we have got 0. Okay, so this is the expectation value of momentum, that is 0. So hope you have understood. Now let's move on to next question. So here is question number 4. So we need to plot graphically Gaussian wave packet. So this is the wave function given here. So then we also have to explain the properties. So these are the properties I have pointed out. So, and this is the graphical representation of this function. So here you see this is exponent. So here e to the power 0, that's going to be 1. If you put at x is equal to 0, e to the power will be 0, and that's going to be equal to 1. If you put here 1, then you will get the maximum value, which is equal to its amplitude, and this is the value of psi at x is equal to 0, right? And amplitude decreases with this sigma, right? This value sigma, and it can be predict from the expression only, and greater value of sigma, the greater the uncertainty, and if sigma approaches to infinite, then Gaussian wave functions becomes flat, right? So these are the properties we have got. So now let's move on to next question. So our next question is, state and prove the Heisenberg uncertainty principle for wave packets if the product of uncertainties in position and momentum is minimum, find the form of function. Also we need to prove here, and also we need to give the statement. So this is the statement. So here you see, so Heisenberg's uncertainty principle states that the product of uncertainties in determining the position and momentum of the particle is approximately equal to a number of order h cut, so which is reduced Planck's constant given by h by 2 pi, h being Planck's constant, right? So this is the expression of Heisenberg uncertainty principle, and these are the terms. Okay, del p, it's uncertainty in the momentum, and del q is the uncertainty in determining the position. So now let's prove this. You see, the standard definition of statistics, applying that the uncertainty in position of particles along x-axis may be defined by this expression. So let it be equation number 1. So then probability of the function finding the particle between the coordinates x to x plus dx given by psi star and psi. So psi star is the complex conjugate of psi, right? Psi star psi dx. So the expectation average values of this x will be given by this expression. This is suppose equation number 2. Similarly, for momentum we have got this expression. Okay, so now let's find the expectation value of momentum, which is given by this result. This is suppose equation number 4, and let us choose a normalized wave function such that expectation value of position and momentum both equal to 0. This is equation number 5. Now to proceed further, let us consider integral. Let us consider this integral, and integrating by parts we have got this result, right? So hope you know how to integrate. So now you see from here what we can do. So integrating by parts, so in the previous slide we have discussed up to this point. Now integrating by parts we have got this result. So now you see psi star psi dx, its integration is equal to 1 for normalized wave function. So this above results becomes, again you see in equation number 6, here in these two parts you will have real and imaginary part, right? Real and imaginary. And if you simplify and if you compare the imaginary parts of both sides, here you see the right hand side is completely imaginary, so it must be equal to the imaginary parts only on the left side. So that's why you will get this result, right? 2i imaginary part of this expression, because in these two cases when you will take the imaginary parts, or in this equation number 6 you will get twice I and the imaginary part of this expression, right? So when you will take the imaginary part, here you will get 2, because if you add the imaginary parts there will be twice the imaginary part. So I hope you can get my point what I am saying, because let me explain again. Here you see, so we have two terms here. It also has real and imaginary, and it also has real and imaginary. When you will add, if you take the imaginary parts and if you add them, then you will end up with the twice imaginary part of this, right? So taking modulus and squaring we get this result. This is suppose equation number 8, and this one is equation number 7 we have taken. And but here you see this imaginary part of this expression, it always be less than equal to itself, right? So this side is imaginary part of this one only, right? And here we have taken the mod of this expression, and on that here you see here, this is the only imaginary part, value of imaginary part we have taken, magnitude of imaginary part we have taken, and here we have taken magnitude of whole expression. So that's why this side must be greater than or equal to the magnitude of the imaginary part only, right? And so from this 8a, since the magnitude, so equation 8a can now be written as this, right? So let me tell you how. Here you see, this is the imaginary part, right? So here you see, as this part is greater, more magnitude of this expression is greater than the magnitude of imaginary part. So if you replace this imaginary part in equation number 8 by this magnitude, then the left hand side will be obviously greater, right? So here you see, instead of this part we have used this part on the left hand side, so then this will be greater, obviously, right? Greater than equal to. So we can express equation number 8 in this form, right? So now and according to Schwarz inequality, we have this relation, and here f star is nothing but this and phi is this, right? And substituting those here, left hand side of the equation number 9, sorry, here you see, on the left hand side of the equation number 9, here what we can write, using 10, that means this inequality, Schwarz inequality, and using those values of f star and psi, phi, the left hand side of equation number 9 becomes this, right? So now therefore the equation number itself can be written as, now let's move on to next slide. So this is the equation number 9 we can write. So and simplifying, we have got this result, and this is nothing but expectation value of p square, and this is nothing but expectation value of x square, and here we have this h cut square by 4. So since expectation value of x is this and that of p square is this, so what we can do, applying the condition imposed by 5, you see 5 to equations 1 and 3. So what was the condition in 5? So let's go to equation number 5. So this is the condition, expectations values of x and p both equal to 0. So if you apply this in 1 and 3, what are the 1 and 3? 1 and 3, if you apply here, then what are you gonna get? So this term will be 0, right? And that's why here you will get this is equal to root over sorry, this will be equal to, as there is a square, so root will be gone with that, and expectation value of x, right? And similarly from here you will get del p is equal to expectation value of p, that's what you will get. So let me explain this part again, that you can see, as we have applied this 5 in 1 and 3, we have got these two, del x is equal to expectation value of x, so you square both sides, then you will get del x square will be expectation value of x square, and from here you will get this, right? And that's what we have done, right? So that's how we have proved this relation. So now this is the proof of Heisenberg uncertainty principle. Now let's go to the last part of this question. What was that? here you see, uh, if the product uncertainties in position and momentum is minimum, find a form of function. So let's go to the last part. Here you see, for minimum uncertainty product, so we have taken here we choose the functions in source inequality, that we have taken those functions in source inequality. uh, Let me tell you here is f and phi. Let me take these two. This f must be proportional to phi, and that's why f must be equal to constant into phi, that is alpha. We have taken the constant of proportionality, and let us choose this function is this, right? And since f the sister, we had taken this one, so f must be taken complex conjugate of that, and phi is x psi, right? And so that equation 2 gives this, this we have taken equation number 2, right? So this one, equation number 2. So using this in 2, we have got this relation, which is equation number 3. Then here you see, we must have inequality sign in equation number 8a, and so we must have the integral. So this result we have got from 8a, so let's go to 8a. This is 8a, right? So this is what we have got in 8a. So this part must be purely imaginary, right? Now you see, for obtaining minimum uncertainty product, we must have equality sign in equation number 8a. So this is the 8a. Let's go back to 8a. So here we must have equal sign for the minimum uncertainty. So that's why if there is the case, then this should be purely imaginary, right? So that's why we have got this. It must be purely imaginary. And here you see, if you use the complex conjugate of equation number 3, here you will get this relation, and from here alpha star is taken outside of the integral, and this is purely imaginary, and this alpha star must be purely imaginary and imaginary number, so that for convenience we may substitute alpha is equal to this equation number 4. This is okay. So now let's go to next slide. So here what we have done, okay, so in equation number 3 we have substituted this alpha star, alpha is equal to I a squared beta. So we have substituted alpha is equal to I a squared beta, right? And we have got this from equation number 3. So this is the equation number 3. This alpha is replaced by this value, and so after simplification and this integration, we have got this result, where this is nothing but a constant of integration, and after simplification we have got this function. This is normalized coefficient. So here you can see magnitude of n can be found out by applying the normalization condition. This is the normalization condition, and if you apply that, if you apply the normalization condition, you will get the value of n. This is the value of n. Here you can see this is the value of n, and if you put this value here, you see, if you put this value here, then you will get the function, right? So this is the function, required function. So hope you have understood this. Now let's move on to the next question. So now question number 5, find out the momentum wave function expression for a free particle in 3 dimensions. So here you see wave function in position is free for free particle is given by this, right? So here P represents momentum, and here this implies a squared k, and that's k is equal to p by h cut, and energy E is equal to h cut omega. So omega will be E by h cut. Omega, angular velocity, right? So now this phi, this is r represents position vector, so that is this is a function of space and time. So if you express this function in terms of momentum and energy, so this becomes, it will take this form, right? So here you see this part of this equation, as it is a function of t as well as p, so we have taken that uh, this is phi of function of p and t, so which is equal to this, right? So let me replace this by this is suppose equation number 1, and if you apply the Fourier transformation, inverse Fourier transformation, we have got this result. So this is nothing but wave function in momentum space for a free particle. In 3D, right? That's what question number 5. That is the answer of question number 5. So hope you have understood this. So thank you for watching. See you in the next video. Stay connected and share my videos with your friends, and hit the thumbs up button. Also hit the bell icon so that you get notified when new video will be uploaded. So see you in the next video. Thank you.